Hello, I will introduce the Ernesto Villacorta theory, called the real gas theory. RGT. Three fundamental concepts are handled for a real gas, which differs from the molecular kinetic theory, MKT, regarding stagnant gas. First, the existence of ordered molecular motion, molecular flow, as a component and in addition to random molecular motion, while heat is being transferred to or from the system. Second, heat transfer as the originating force of that ordered molecular motion, either in the expansion or contraction of the gas, and lastly, the non-ideality of the gas is mainly due to the portion of transferred heat energy converted into additional kinetic energy that the ideal gas does not take into account, or rather, by not considering it, that value is short or exceeded. Although the non-ideality affects the entire process, it is not exclusive to movement, it is in the movement where it impacts practically in its entirety. The portion of heat energy converted to kinetic energy is called the momentum enthalpy. The adjustment to the ideal gas so that it behaves like a real gas is called the residual enthalpy, and the equation obtained, its product, is called the residual enthalpy equation. When the ideal gas behaves the same as the real gas, then the residual enthalpy is equal to 0, and when the ideal gas deviates from the real one, it is the adjustment that levels the relationship. The nature of the molecule intervenes in its energy conversion capacity, from calorific to kinetic. That is, intermolecular forces impact non-ideality, but the best way to take it into account is through the heat transfer mechanism. So, oxygen, for example, has a different energy conversion capacity than nitrogen, as well as a different heat capacity and thermal conductivity. The so-called equations of state are supported by factors that work inconsistently. That is, they can work well, but only for specific pressure and temperature ranges. Some may work satisfactorily for most cases but will inevitably deviate from the real value for some conditions or compounds. This is because these equations do not fully describe the thermodynamic phenomenon. Another way to visualize the expansion and contraction of a gas is presented here. Conventional texts handle the expansion of gas as a product of the increase in its temperature, resulting from an increase in the kinetic energy of its molecules, and the contraction as the reverse process. This is universally accepted, and this work is no exception. The divergence with this theory consists of the trajectory these molecules follow when they are excited. By convention, it is accepted that these molecules collide and travel in a disordered way in random directions. Their trajectory depends only on the collision, and therefore the pressure is the product of millions of collisions with the walls of the container. RGT maintains that this is only partially valid. In addition to random movement, to this, we must add an ordered movement whose trajectory will depend on the geometric shape in which heat is being transferred to, or from the system. Pressure changes are also related to the acceleration and deceleration of molecules. Let us consider the following. Suppose you have a container 3 meters high and 2 meters in diameter with a 2-inch nozzle. This tank has any gas at a specific pressure. Under this scheme, the nozzle area represents only 0.02% of the total internal area of the tank. The assumption that random collisions with the wall generate pressure suggests that, at the moment of opening the nozzle, the gas contained inside will come into contact with the outside, and, consequently, the tank pressure will decrease because some of the gas molecules inside collide with each other and will come out through the hole as a consequence of a momentum generated by the collisions. How in a tank a system goes from being a chaos to being an ordered system only by passing through a hole? Because, while the nozzle itself could be the channeling of molecules, it would be at short distances between them and lower speeds, not at the random distances and speeds at which the molecules of a gas move in the MKT. That is, it would be at a distance between molecules and their velocities of a molecular flow, not of a random movement. How is it possible that there is an orderly movement coming out of the nozzle instantly if there is chaos inside? What is the probability that a molecule will leave by 0.02% of a total area due to random collisions? Is that probability proportional to the rate at which pressure is released in the tank? In this work, it is argued that, on the contrary, when excited molecules undertake trajectories with defined tendencies towards a certain geometry. This geometry depends on the spatial form in which heat is being transferred so that the molecule will take the opposite direction as the heat transfer. The RGT states that chaos was ordered in density and pressure transient profiles, before passing through the hole. Let us imagine a gaseous sphere of mass, m, that is subjected to the action of a heat source Q. This sphere has an initial volume VO, and through the action of heat increases its volume to Vf, at a constant pressure. Located on the edge of Vo, what can be seen is the movement of a vector normal to a plane with a velocity during a time t. From the macroscopic point of view, this physical phenomenon can be considered a concentric flow stimulated by a change in density in the concentric layers, where the density and enthalpy profiles are generated by the temperature differential resulting from heat transfer. Figure 1.1 shows this system. These transient profiles could be seen as expansive or contractive waves like water waves whose velocity is a component of total molecular velocity. Like balls bouncing inside a truck that moves slower than them, that group of molecules already experience intermolecular forces, due to their proximity, so that these molecules travel in a group, apart from random movement, and behave already as a molecular flow. Like any fluid flow, its molecules have the velocity of flow and the molecule's speed that make up it. The profiles are defined as transient because they fall apart eventually, and the molecules that formed them will separate. The formation of transient profiles could be visualized as an equivalent phenomenon to when air is fanned. This creates profiles formed by the momentum transmission generated by the propellant object, but the gases that make up the mixture are elastic and eventually, the molecules recover the separation between them. The velocity of the flow generated by the propellant is usually much lower than the random molecular speeds of its molecules. The validity of MKT has been confirmed in different ways, for example, the rate of reaction in chemical processes. It is important to say that the RGT, rather than being an objection to MKT, it is a complement to this theory. It helps to explain circumstances that the MKT cannot explain, such as the case cited regarding the tank. On the other hand, suppose you have a stoppered flask subjected to a heat source through the glass boundary. According to collision theory, the heat causes a molecular excitation in the contained gas leading to numerous shocks against the glass, which would cause the pressure to increase to the point of fracture of the glass. Now, if the procedure is repeated but with the flask uncovered, it would be assumed that the event would be the same since the collisions are due exclusively to molecular excitation. However, the reality is that, under the latter conditions, the flask does not fracture. Why? What is the reason that prevents the flask from breaking? If the collisions and trajectories are assumed to be totally random, they do not depend on the presence of a stopper. Furthermore, if we grant that the excited molecules exit through the hole instead of hitting the glass, how do we explain when they stop coming out of the hole? This question cannot be answered by collision theory. MKT cannot explain how the leakage of molecules in an open flask, subject to a heat source, is stopped eventually. The explanation can only be given through a connection between the microscopic and macroscopic vision of the aforementioned phenomenon. That is, the equilibrium between two momentum-generating forces, the pressure differential dP and that of the momentum enthalpy, and this is because, the formation of transient pressure and density profiles. For MKT this does not happen because of random movement, separation between molecules and the absence of intermolecular forces, but neither does it explain how it is that the molecules at a certain moment stop leaving the flask, or how they be ordered from the chaos before leaving the tank, as it happens in reality. The RGT explains this through the formation of transient profiles, and this, if and only if, there is heat transfer to or from the system. That is, in the absence of heat transfer, such profiles are not formed. As a result of an energy balance that we will see later, we obtain the differential of the momentum enthalpy. The negative sign in the equation means that the direction of the velocity vector is opposite to that of the heat transfer. So how to explain the phenomenon that occurs inside the flask shown above? The transferred heat generates transient profiles of density, enthalpy, and pressure, as shown in figure 1.6. This creates two opposite forces. The first is represented by the differential of the momentum enthalpy and the second can be defined as the momentum generated by a change in gas pressure called Euler's equation with the opposite sign to the momentum enthalpy differential. So that both forces generate the balance to avoid the fracture of the glass and it establish that there is a limit on the leakage of molecules from the open flask. In figure 1.6. As the temperature continues to rise, a point will be reached where the outward directed momentum will dominate over its counterpart, and the glass will fracture because the plug does not allow pressure to be released. The molecules will push each other transferring momentum to the glass causing its fracture. For the unstoppered flask in figure 1.7. The system is the same with the difference that pressure is released through the orifice by allowing gas to escape until the pressure equalizes with atmospheric pressure. And molecules do not reach necessary momentum magnitude to cause the glass fracture, due to the action of its counterpart. The rest of the gas does not leave because it is in equilibrium. The energy balance on the model, the convection diffusion equation, and the residual enthalpy equation EER. Applying the energy balance on a model, the energy change within the system accounts for three types: internal energy, kinetic energy, and potential energy. The energy of the surroundings consists of the heat transferred and the work done, shown in equation 1.1 or 1.2. Equation 1.3 shows how the heat is conformed. The heat is composed of the enthalpy of the gas delta H, the momentum enthalpy, which is the portion of heat energy converted to kinetic energy, delta Hm, and the adjustment between ideal gas and real gas, delta Hr, which is called residual enthalpy. When the ideal gas behaves like a real gas, then the residual enthalpy is equal to 0. But when the ideal gas moves away from the real gas behavior, the heat Q is equal to the residual enthalpy plus delta Hg, like it is shown in 1.3a. Delta Hg is the amount of the caloric energy transferred for a real gas. Whence delta Hg is composed by the enthalpy of the gas and momentum enthalpy delta Hm, like it is shown in equation 1.3b. It is important to remember that delta Hm represents the quantity of energy destined to molecular movement. Introducing the internal energy in equation 1.4. For the case where delta Hr is equal to 0, and considering only the work done by the mass of the fluid, then W equal to delta PV in a process at a constant pressure, where, in addition, the effects of gravity will be conveniently neglected. If we combine equations 1.3 and 1.4 with equation 1.2, we have equation 1.5. In differential form, we get equation 1.6. For a system of mass m we obtain equation 1.7, and for a system of density ρ we get equation 1.7a. It is recalled that equation 1.7a is the same as we saw in the previous section for the case of the equilibrium in the flask, and that the negative sign in this equation means that the direction of the velocity vector is opposite to that of the heat transfer. For heat subtraction, the directions of the vectors are the opposite. We can use the convection diffusion equation to explain the concept of momentum enthalpy and residual enthalpy. Equation 1.9 is presented in two dimensions. The version of equation 1.9 for one dimension and applied to the ideal heat energy gives equation 1.10. In equation 1.10, the first term on the right is the ideal caloric term, and the second is the ideal caloric inertial term. The heat energy for a real gas is given by equation 1.11. In equation 1.11, the first term on the right is the real gas caloric term, and the second is the real gas caloric inertial term. And it's important to notice that this last term is the momentum enthalpy, that is the amount of caloric energy converted in kinetic energy of gas molecules. The combination of equations 1.10 and 1.11 with equation 1.3 results in equation 1.12. The RGT maintains that, although the non-ideality of gas affects the entire process, it is in molecular motion where it manifests itself practically in its entirety. That is why it is considered that ideal and real caloric terms have very similar value, like shows equation 1.13. For the inertial terms, the same assumption cannot be made, therefore, equation 1.13 is combined with equation 1.12 to get equation 1.14. If the ideal heat energy is equal to that of the real gas, that means that the heat kinetic energy conversion would be the same between both, which in turn means that there would be no residual enthalpy delta Hr, and then, the caloric kinetic terms would have the same value like the one shown in equation 1.15. Residual enthalpy delta Hr per time unit is definitely related to the kinetic energy of the system and is the adjustment that levels the relationship between ideal and real gas. In the box is shown the possible circumstances for delta Hr, and in figure 1.8 are presented drawn. That is, if delta Hr is greater than 0, then, it means that the ideal inertial term is greater than the real one, in figure 1.8 is shown like the vector of the ideal term is greater than the real one. If delta HR is less than 0, then real inertial term is greater than the ideal one. In figure 1.8 is shown like the vector of the real term is greater than the ideal one. If delta HR is equal 0, then both terms are equal and so their vectors. The way to relate the parameters P, V, and T with the residual enthalpy, delta HR, is the residual enthalpy equation EER, which is presented in equation 1.16. Considering moles and mass, we get equation 1.17 or equation 1.18. Notice that equation 1.19 shows that the adjustment of the ideal gas in order that it behaves as a real gas, called delta HR, is circumscribed exclusively to molecular motion, that is an adjustment of kinetic energy of the gas. As we look to in equation 1.14. That's why equation 1.16 is called EER. 6 versions of the EER are presented according to the type of process: process at a constant P, process at constant V, and process at constant temperature. These equations are from 1.20 to 1.25. Where P superscript O, V superscript O and T superscript O are the corresponding parameters as an ideal gas. And the subscript number 2 means that the corresponding parameter belong to state 2. Examples solved with different equations of state. Constant volume process. Let us suppose an identical system described in figure 1.1, but now with a solid border as a container. The velocity of the furthest layer is equal to 0. For demonstration purposes, thermal conductivity is neglected in this border. We are looking to describe the thermodynamic phenomenon inside the sphere, not at the border. For an ideal gas, the internal energy is a function of temperature only, so enthalpy and Cp are 2. That is the reason why the heat may be obtained with equation 2.31. This is for all types of processes, not only the constant pressure process. Example 2.1. Nitrogen gas at 85 Ca will be heated from 276 degrees Kelvin to 292 degrees Kelvin with a constant volume V equals 2.2336 cubic feet. We want to know the final pressure. We take the system as 1 pound mass of gas, contained in an imaginary sphere container. We have the following information from nitrogen thermodynamic tables. From equation 2.31 we obtain the amount of heat Q superscript O. The amount of heat, delta Hg, for real gas is obtained by subtracting the enthalpies of states 1 and 2. Using equation 1.3a with the calculated amounts of Q superscript O and delta Hg we obtain the residual enthalpy, delta Hr. The pressure for the ideal gas is obtained as usual. Substituting these values with the information gotten in equation 1.23, it results in obtain the pressure for real gas in state 2. The reported experimental datum for pressure is 90 Ca. Constant pressure process. Example 2.2. Nitrogen gas increases its volume at a constant pressure of 85 Ca when heated from 254 degrees Kelvin to 350 degrees Kelvin. We want to know the final volume, whose experimental value is 2.84 cubic feet, if the initial volume is VO equals 2.052 cubic feet. We take the system as 1 pound mass of gas, see figure 1.1. We have the following information from nitrogen thermodynamic tables. So, we get the amount of Q superscript O, delta Hg and delta Hr the same way as in the previous example. The ideal gas volume is calculate as usual. Substituting these values with the information gotten in equation 1.21, it results in obtain the real gas volume. This value is equal to the datum reported for the experimental volume. Table 2.1 shows several data for the volume obtained by different equations of state for a given temperature and pressure. The equations used are the ideal gas equation, and we abbreviate it as ideal. The van der Waals equation is abbreviated as VDV. The Redlich-Kwong equation is abbreviated as RW. The Soave-Redlich-Kwong equation as SWR. The Peng-Robinson equation as PR. And finally, The equation of this theory, the residual enthalpy equation, as EER. And all these equations are measured, that is, compared to the experimental data reported, that are abbreviated as EXP. As shown in Table 2.1, the range of greatest deviation in relation to EXP is at high pressure and low temperature, as expected, with one exception, the EER, which maintains the similarity with EXP all the range. It can also be seen that these mathematical correlations adjust to EXP only for a part of the range, but for the rest, they deviate irremediably. This happens because these equations do not fully describe the thermodynamic phenomenon. For example, we chose conditions like high pressure and low temperature. It is the state at T equals 100 degrees Kelvin and P equals 100 Ca. The experimental datum for volume under these conditions is 0.583 cubic feet. For ideal, it is 0.689 cubic feet. Its deviation from EXP represents an 18% error. For VDV, the volume is 0.611 cubic feet, which represents a 4.80% error. RW presents a volume of 0.626 cubic feet and a 7% error. SRW got 0.591 cubic feet, 1.37% error. For PR, the volume is 0.631 cubic feet with an 8% deviation error. Finally, EER got a volume of 0.583 cubic feet, which represents a 0% error. Therefore, the value obtained by EER and the one of EXP are the same. Figure 2.3 shows the graphic, for the data of Table 2.1. Pressure versus volume at 100 degrees Kelvin for ideal, EER, and EXP data. The figure 2.4 shows the graphic for the data of Table 2.1, as well, but now for pressure versus percent error volume. Percent error volume means the percentage of deviation of the volume, obtained for a given equation of state in relation to the volume reported as experimental data. In Figure 2.4 we can see how the ideal gas equation deviates markedly as pressure increases, but it is not the only one. What should be noted here, is how the residual enthalpy equation EER remains constant all the time at an error rate very close to 0%. Figure 2.6 shows the diagram of pressure versus percent error volume, but now at T equals 181 degrees Kelvin. What we can see is that, for this temperature, deviations of some equations of state with EXP are not already as great as the presented for T equals 100 degrees Kelvin, where the percent error is such that it exceeds the percentage allowed by numerical simulations in numerical analyses. The average percent error of volume x percent E is the sum of each percentage for a given pressure, divided by the total number of graphed data for each equation of state, where n is the total number of graphed data from 14.7 Ca to 100 Ca, for this case. N equals 10. Figure 2.7 shows a graph of the average percent error of volume for the mentioned above equations of state. Here we can notice how great is the difference between EER and the others' equations. Figure 2.8 shows a graph of the average percent error of volume for the same equations of state, but now at T equals 181 degrees Kelvin. In figures 2.7 and 2.8, we can see how average percent errors of volume change drastically from 100 degrees Kelvin to 181 degrees Kelvin. That is called inconsistency, with only one exception, the EER equation. Figure 2.9 shows the inconsistency of equations of state, IES, and how they change at one temperature compared to another, in this case, at 100 degrees Kelvin and 181 degrees Kelvin. It shows, too, the consistency of EER. A good way to measure inconsistency of equations of state, IES, is applying the derivative of the average percent error of volume with respect to temperature. Figure 2.10 shows a comparison of the inconsistency of the equations of state. In summary, it can be concluded that the EER differs greatly from the rest of the equations of state in terms of its accuracy in describing the behavior of the real gas. Molecular velocity of the momentum enthalpy delta Hm, molecular flow velocity, in feet per second. Molecular velocity of the momentum enthalpy delta Hm, molecular flow velocity, in feet per second. As already said, the molecular velocity of the momentum enthalpy, molecular flow velocity MFV, is a component, together with the random molecular speed, that make up molecular kinetic energy. To obtain the molecular flow velocities in feet per second, some assumptions need to be made. To begin with, it is considered an imaginary gaseous sphere, as a model, as presented in Figure 1.1. In addition, the velocities considered are those of the layers farthest from the center, that is, those of the boundary of the sphere. And finally, it is defined that the heat transfer process, temperature change, takes place in a period of 1 second. Therefore, the change in the volume of the gas with respect to time is defined as it shown in equation A.1, where r is the radius of the gaseous sphere, see figure A.1. So that the molecular velocity of the momentum enthalpy delta Hm, MFV in feet per second may be obtained by the equality defined in equation A.2a. Figure A.2 shows the velocity vector tangential to the circumference. Another geometric figure may be a cube, for example, like is shown in figure A.2. The molecular flow velocity for a cube may be obtained with equation A.2b, where L is the side of the cube. Note that the MFV, V, will have different value, according to the geometric figure, for the same volume differential, dV. Although the procedure cited here is standard, that of equations A.2a and A.2b, the words, momentum enthalpy, are added, because the final volume that is used here, is the one as obtained by the EER. Example A.1. We have 1 pound of 5 cubic feet nitrogen at 14.7 Ca. At these conditions the gas is at 110 degrees Kelvin. In the other side there is 5 cubic feet of 1 pound of oxygen with the same pressure at 124 degrees Kelvin. Both gases are subjected to a heat source of 2545 BTU per pound mole, for an expansion at constant pressure. It is important to emphasize here, that Q superscript O, subscript TO, is the heat as a function of the temperature of the ideal gas. Different from that function of heat of examples 2.1 and 2.2, that is the heat as a function of the temperature of the real gas. Determine the momentum enthalpy molecular flow velocities, MFV, in feet per second. The incomplete scheme is the one as shown. Nitrogen and oxygen information is taken from thermodynamic tables. Figures A.3a and A.3b show the distribution of its respective heat capacities. We use a mean heat capacity, as the one written in equation A.3. By using equation 2.31, we may have the final temperature of nitrogen as an ideal gas, that is 311.8 degrees Kelvin. Then the final volume of nitrogen as an ideal gas is 14.17 cubic feet. The final temperature of oxygen as an ideal gas is 325.7 degrees Kelvin. Then, the final volume of oxygen as an ideal gas is 13.13 cubic feet. With the temperatures gotten, and using them in the thermodynamic tables of nitrogen, we have that the delta Hg is 2544.5 BTU per pound mole. The delta Hr is obtained by the substitution for delta Hg in equation 1.3a, this amount gives 0.5 BTU per pound mole. With the temperatures gotten, and using them in the thermodynamic tables of oxygen, we have that the delta Hg is 2544.6 BTU per pound mole. And the delta Hr gives 0.4 BTU per pound mole like it is shown in equation A.7. Applying equation 1.21, the final volume is 14.176 cubic feet. And the final volume for oxygen is 13.134 cubic feet, as it is shown in equation A.9. The final temperatures for real gases are 311.87 Kelvin for nitrogen and 325.72 degree Kelvin for oxygen. Finally, the complete scheme is presented. Therefore, the volume change per unit of time is 14.176 minus 5 is equal to 9.176 cubic feet. Taking as volume that of an imaginary sphere, the radii for states 1 and 2 are 1.0608 feet for radius of state 1, and 1.5013 feet for the radius of state 2. From equation A.2a, and incorporating the corresponding information, we have that the molecular flow velocity is 0.3239 feet per second, as shown in equation A.10. For oxygen, the volume change per unit of time is 13.134 minus 5, is equal to 8.134 feet per second. The radius obtained for state 2, of the sphere is 1.4636 feet. The momentum enthalpy molecular velocity, MFV, is 0.3021 feet per second. It exists a relationship between the molecular velocity MFV, and the final volume, in a process. Since the MFV of nitrogen is greater than the one of oxygen, then the final volume of nitrogen is greater too than the final volume of oxygen. The fact is, that the greater the distance traveled in a period of time, the greater the area covered. Example A.2. 1 pound of hydrogen in an initial volume of 65.3 cubic feet at 14.7 Ca. At these conditions the gas is at 100 degrees Kelvin, is subjected to a source of heat energy of 2545 BTU per pound mole, for a constant pressure expansion. Calculate the MFV in feet per second. From hydrogen thermodynamic tables we get the delta Hg and the Cp. See figure A.3. The final volume as an ideal gas is given in equation A.12. And the residual enthalpy in equation A.13. Therefore, the final volume of hydrogen is 194 cubic feet as shown in equation A.14. And the final temperature for the real gas is 297.1 degrees Kelvin. The complete scheme is presented. The radius for state 2, obtained from the sphere is 3.5911 feet. The volume change per unit of time is 194 minus 65.3, equal to 128.7 feet per second. The molecular flow velocity is 0.794 feet per second as shown in equation A.16. Example B.1. Several gases are subjected to the same process to make a comparison. The process consists of a constant pressure expansion at 14.7 Ca. To accomplish this, 1 pound of gas in 10 cubic feet is subjected to a heat source of 2500 BTU per pound mole, to then be subjected to a contraction by removing negative 2000 BTU per pound mole of heat energy. A. Make a comparison of gases. B. Repeat the comparison of point A, for different pressures. C. Determine the MFV for the gases. Figure B.1 presents the data obtained. To obtain data in figure B.1, the calculation was made with the tools of RGT that we have seen here. The subscript O means that it belongs to the initial state, the subscript 2 means that it belongs to the final state for expansion but the initial state of contraction as well. And the subscript F means that it belongs to the final state of contraction. An efficient tool to compare the performance of gases, it is what we call here the elasticity index E. And it is closely related with the MFV, it is presented in equation B.1. Parameter M subscript WCPM is the molecular weight multiplied by an average of the expansion-contraction heat capacity. Table B.1 shows information for a pressure of 1 atm. It is a comparative table of parameters for different gases for 1 atm. From the observation in table B.1, we have that the greatest elasticity index is the one for nitrogen, followed by the one for carbon monoxide, then the next is the argons, the next is the oxygens, and the last, the smallest, is the one for carbon dioxide. The same order is held for molecular velocities MFV. But, for the parameter m subscript WCPM, the order is exactly the contrary. The greatest is the one for carbon dioxide, followed by the one for oxygen, then the next is the argons, the next is the carbon monoxides, and the last, the smallest is the one for nitrogen. Table B.2 shows the information for a pressure of 4 atm. From the observation in Table B.2, we notice that order has changed. Now, the greater elasticity index is the one for argon, and smallest one is for carbon dioxide. The MFV follows exactly the same order as the elasticity index, that is, now, the greatest MFV is for argon and the smallest for carbon dioxide. And for the parameter m subscript WCPM, the order is exactly the contrary to the one for elasticity index and MFV. For a constant pressure of 7 atm, the order is presented for the three parameters compared. And for 10 atm of constant pressure, things do not change with respect to the order in which they have been presented for the system at 7 atm. Figure B.2 shows the elasticity index functions for the gases handled here. For different processes of constant pressures. Figure B.3 shows the MFV functions. For the handled gases, it is important to notice that the trend that follow both functions, the elasticity index and the MFV, is practically the same. Both have in the point of 4 atm, a drastically change in the function slope. Furthermore, if we observe the figures B.4 and B.5, we can notice that the volume function in the expansion and contraction processes behave the same as MFV and elasticity index functions. Why? And another question is, if they all gases have the same initial volume, the same mass, the same constant pressure, and they all are subjected to the same heat source, why they have different final volume? We can observe the following. The trend followed by the functions of gases is the same. The order followed by the functions of the gases, among them, is the same. 4 atm is clearly the point of divergence between the functions of the gases. And it is the pressure, at which the trends in the functions of gases, argon, nitrogen, and carbon monoxide, get distance of themselves from each other, with respect to the measured parameters. This is due to the Cp, as we will see later. The point at 4 atm also establishes a marked change in the rate of change of the graphed functions of the gases. This is because of the relationship PVT, as we see later. In the diagram, pressure versus MFV and the diagram pressure versus elasticity index, the pressure is inversely proportional to both the MFV and the elasticity index. The higher the pressure in the system, the lower the molecular flow velocity and the lower the elasticity index of the gas. Figure B.6 shows that, for the 1 atm system, the ratio between temperatures is almost twice the magnitude of T2 with respect to T1, until reaching the 10 atm system, where the proportion was reduced to almost unity. That is, at 10 atm the ratio between temperatures changes very little, so the volume also changes very little. But this change is not gradual, but the ratio between the magnitudes of T1 and T2 temperatures is abruptly reduced in the system to 4 atm. That behavior is already defined by the PVT relationship. In figure B.7 you can see the PVT behavior of argon gas. This figure shows the isotherms in the PV diagram. It can be observed that at 4 atm point an abrupt change comes, with respect to the trajectory that the volume function will follow for the following systems of 7 and 10 atmospheres. The other gases have diagrams very similar to this. The point at 4 atm appears in all the graphs that we have studied as a point of change in the trend of the functions, and the reason is, because this is how the PVT relationship defines it for the handled gases. That is, the tendency is already established by the PVT diagram. Suppose, for example, a process by which the temperature of the gas is increased from 200 degrees Kelvin to 600 degrees Kelvin, at 1 atm, then another process with the same temperature range, but now, the system at 4 atm, another at 7 atm and finally one at 10 atm. Figure B.8 shows the scheme for this case. The delta V is the isobaric line and shows the segments of final volume minus initial volume obtained for each system, from 1 atm to 10 atm. The proportion between segments is presented in equation B.2a. We can clearly see that, since the point to 4 atm, the trend in the reduction of volume segments changes markedly. This case is similar to the example, which we have been discussing, with the difference that example B.1 reaches temperatures up to 3314 degrees Kelvin. And, in addition, that the initial volume is 10 cubic feet, on all systems. For the other gases the trend is the same, although the segments delta V are of different sizes. That is, the final volumes Vf are different. It is more notorious from the point at 4 atm. B.9 shows the 200 degrees Kelvin and 600 degrees Kelvin isotherms for argon and carbon dioxide. You can clearly see the same trend and also the difference between the volume segments between argon delta V and those of the carbon dioxide delta V. It is concluded that the PVT relationship define the trend of the function, but the size of the segments of the isobaric line is defined by the nature of the gas. That is, the capacity to convert caloric energy into kinetic energy will define temperature in state 2 and then volume of state 2, so that the argon segments are greater than the ones of carbon dioxide. The molecular kinetic theory MKT. The mean molecular speed VMS in feet per second. Joule's experiments on heat, as well as Bernoulli's investigations, served as the basis for Joule, Clausius, Maxwell, and Boltzmann to develop the MKT, in the period between 1848 and 1898. Also known as kinetic theory of gases, which is based on the idea that all gases behave in the same way as far as molecular motion is concerned. The validity of MKT has been confirmed in different ways, for example, the rate of reaction in chemical processes. It is important to repeat, so that it is clear. RGT, rather than being an objection to MKT, is a complement to this theory. For example, it explains circumstances that the MKT cannot explain, such as the case cited in above section of the RGT regarding the flask, and why MKT cannot explain how the leakage of molecules in an open flask, subject to a heat source, is stopped eventually. Or how in a tank, a system goes from being a chaos, to being an ordered system only by passing through a hole, because, while the nozzle itself could be the channeling of molecules, it would be, at short distances between them and lower speeds, not at the random distances and speeds at which the molecules of a gas move in the MKT. That is, it would be at a distance between molecules and their velocities of a molecular flow, not of a random movement. These explanations can only be given through a connection between the microscopic and macroscopic vision of the aforementioned phenomenon. And that is, the equilibrium between two momentum-generating forces. Pressure differential dP and that of the momentum enthalpy, delta Hm, for the case of the flask. And in the case of the tank, that chaos was ordered in transient profiles before passing through the hole. How to relate both theories? How to relate the mean molecular speed VMS, of MKT, with momentum enthalpy molecular velocity, MFV, in feet per second. How to explain the huge difference in magnitudes between the two. Two of the equations that make up the MKT are A.17 and A.18. Where E subscript Mk is the molecular kinetic energy of the MKT, T is the ideal gas temperature T superscript O, and M subscript W, is the molecular weight. From a simple analysis, it is concluded that the parameters involved in the MKT are related by a constant of proportionality K superscript O, between state 2 and state 1, or K, for real gas. This constant, in turn, represents the connection between the microscopic and macroscopic state. Represents the connection between MKT and RGT. Relates the mean molecular speed of MKT VMS, with the momentum enthalpy molecular velocity, MFV. In the box is shown the equations that relate state 1 and 2 by the constant K superscript O. For kinetic energy, equation A.19. For molecular speed, equation A.20. For the volume, equation A.21, and finally, for the temperature, equation A.22. MKT is based on ideal gas concepts. The superscript is used in the constant K superscript O, because it represents an ideal gas-based constant. It is also based on 1 pound-mole, but for purposes of the constant, which is a quotient, it is dimensionless. The real gas constant K is obtained from the division of the temperatures of real gas, gotten with the EER, and can be simply substituted for K superscript O in equation A.20 to obtain real gas speeds, because this equation, although it belongs to the ideal gas, does not require an additional procedure to obtain real gas values, as will be shown later. And this happens because the RGT maintains that non-ideality manifests itself practically in its entirety, as a thermal phenomenon. And therefore, since temperature is the only variable that defines the mean molecular speed, then, by applying the real gas temperature to equation A.17, you get the mean molecular speed for real gas, V superscript R, MSR. MKT assumptions for molecules have constant and random speed, linear motion. They are separated from each other. They collide with each other. No intermolecular forces act. As a whole and within the system for the entire process comply with delta U equals 0. The constant K superscript O is the ratio of the mentioned parameters, state 2 divided by state 1, in each parameter for an ideal gas. It relates both states, as does RGT with elasticity and MFV. The constant K is exactly the same but for real gas parameters. The equation A.23 relates the mean molecular speed of MKT, VMS with the momentum enthalpy molecular velocity, MFV, for states 1 and 2. Using the imaginary gaseous sphere as model, or using a cube, where V superscript R subscript MS is the mean molecular speed for real gas. The subscripts 1 and 2 refer to states 1 and 2 of the process. How to relate both theories, the MKT and the RGT. As already stated, only the macroscopic perspective can explain the flask and tank phenomenon described above. And that is, the formation of transient pressure and density profiles. The MKT holds that the path of the molecule is constantly altered by collisions with other molecules, see figure A.4. For RGT, the acceleration of molecules product of heat transfer produces collisions, that generate transient accumulations and therefore the proximity between them, which activates the intermolecular forces, and thus, conform the molecular flow, whose direction is contrary to heat transfer, as described in figure 1.4. Considering that the molecules already have a random movement before heat transfer starts, with their respective molecular speeds Vms. Once it begins, the transient profiles are formed and the molecular flow starts at a velocity in the order of 4,300 times lower than the mean molecular speed for certain conditions of gases, such as nitrogen, oxygen, and argon, and begins the described mechanism in figure 1.4. Behaving already as a molecular flow. Like any fluid flow, the profiles are defined as transient because they fall apart eventually and the molecules that formed them separate. The proportionality between the mean molecular speed of the MKT, VMS, with the molecular flow MFV, at certain PVT conditions, is presented in equation A.24. With a rough calculation, we state that the distance between molecules is reduced at a similar proportion, as it is presented in equation A.26. Equation A.26 shows an idea of how much the distance between molecules is reduced transiently. This temporary reduction should not be seen as a conventional compression of the gas. First, because a generated molecular momentum is involved. Second, because it is only a group of molecules, and third, because the gas is elastic and eventually the molecules will recover the original distance between them, and even increase it, in the case of expansion. For contraction the process is reversed, for example, the vector's orientation, etc. Example A.3. Determine the momentum enthalpy molecular velocities, MFV, in feet per second. From example A.1, with the mean molecular speeds. Example A.1 shows that the MFV of nitrogen is equals 0.3239 feet per second, and the MFV of oxygen is equals 0.3021 feet per second. The nitrogen temperatures in example A.1, in Rankine are T1 equals 198 degrees Rankine and T2 equals 561.36 degrees Rankine. Using equation A.17 and with equations A.27 and A.28 we can obtain the mean molecular speeds. And with equation A.23, and using the radii of example A.1, we have that the molecular flow velocity is calculated in equation A.29. This is exactly the same result as the one obtained in example A.1. The oxygen temperatures in example A.1, in Rankine are T1 equals 223.2 degrees Rankine and T2 equals 586.26 degrees Rankine. With equations A.30 and A.31 we can obtain the mean molecular speeds. Using the radii of example A.1, we have that the molecular flow velocity is calculated in equation A.32. Example A.4 calculate the hydrogen mean molecular speeds gotten in example A.2, but now with the MFV in the expansion process. By ideal gas. By real gas. The information we have from example A.2 is: the MFV of hydrogen is 0.794 feet per second, V1 equals 65.3 cubic feet, R2 equals 3.5911 feet, T1 equals 180 degrees Rankine, T2 equals 534.6 degrees Rankine. And T2 superscript O equals 516 degrees Rankine. R1 is obtained with equation A.33 and is 2.498 feet. Using equation A.23, and solving for K, the equation A.34, we get that K equals 2.9707. The mean molecular speed for state 1 is 3666.66 feet per second. The mean molecular speed of real gas in state 2 can be obtained with equation A.20, using the real gas constant K, and is may be written in equation A.36. And has a value of 6,319.59 feet per second. We can also use equation A.17 with the temperature T2 as presented in equation A.37, which is the same result got in the immediately preceding calculation. This finding is fundamental to verify what has been said in RGT. That the non-ideality of gases lies mainly in a phenomenon of a thermal nature, rather than of a volumetric nature. Or rather, the volumetric effect is a consequence of the thermal effect, and the ratio K superscript O divided by K, is a measure of the non-ideality of gases. For the ideal gas, we obtain the constant for ideal gas with equation A.38. The mean molecular speed of state 2 for ideal gas is obtained with equation A.20 using K superscript O and has a value of 6,208 feet per second. As it is shown in equation A.39. We can also use equation A.17 with the temperature of the ideal gas in state 2 like it is written in equation A.40 with the same result as equation A.39. The magnitude of the mean molecular speed for ideal gas deviates from its equivalent one for real gas in such a proportion, which is the same proportional deviation by which it deviates V2 of V2 superscript O, obtained with RGT. This reaffirms what is stated here in the sense that the validity of the constants K and K superscript O is checked, as well as the relationship between them. And the validity of the link between MKT and RGT is confirmed. This is written, as shown in equation A.41. How to relate this to RGT? The next schematic describes how RGT relates with MKT, using equation A.41 and equation 1.21. Equation A.43 shows the relationship between the MKT and the RGT. The ratio between molecular velocities, the random mean molecular speed divided by the molecular flow for hydrogen, is different to that of the gases handled in the previous examples, is about 6,000. In summary, for MKT the only distinguishing factor between the different gases, with respect to mean molecular speeds equation A.17, and therefore to their molecular momentums, apart from temperature, is their molecular mass. For the RGT there is no problem with that. The difference between MKT and RGT arises, first by the adjustment to real gas, but above all, by the formation of transient profiles. For MKT, they do not exist, it does not consider them. RGT considers that the transient profiles of the gases distinguish one gas from another, as a consequence of the distinction between their momentum enthalpies delta Hm. These profiles generate the difference between expansion velocity, MFV, of the different gases, and consequently, their final volumes for the same initial mean molecular speed, see example B2, the same initial volume, the same mass and the same constant pressure, and subjected to the same heat source. For MKT the mean molecular speed is directly connected to the volume by the constant K superscript O by the equation A.20, but this explains neither the Flask phenomenon, nor the difference between specific heats, nor the difference in expansion velocities of the different gases. For RGT the difference between expansion velocities of gases is closely related in addition to molecular masses, to the difference between specific heats and difference between calorific kinetic energy conversion capacities, delta Hm. These last two properties of the gas only make sense through the formation of transient profiles. And they are a reality, just as it is, that in a flask subject to a heat source there is no perpetual leakage of molecules. Finally, the non-ideality of gases lies mainly in a phenomenon of a thermal nature, rather than of a volumetric nature. The difference between ideal gas volume and real gas volume is a consequence of the delta Hr, but it is not the cause of non-ideality, and the ratio K superscript O divided by K is a measure of the non-ideality of gases. The cause of non-ideality is the portion of converted kinetic energy that didn't take into account from a heat source. Example B.2. Analyze the effects of pressure on the mean molecular speeds, VMS, in example B.1. With the use of the equations from A.17 to A.23, the data shown in the tables B.3, B.4, B.5 and B.6 are obtained. An imaginary cube is used as a model. Note that in example B.1 the sphere was used as a model. The first thing can be observed from the data in the tables, is that for each system for the expansion process, the mean molecular speeds of state 1, of all gases are very similar to each other, although their temperatures are completely different. This is because the quotient T/MW is equal for all gases in state 1. So, for state 1 and only in the instant before the heat transfer starts, the term for the kinetic energy in the EER equation is equal 0. Then, the equation is reduced to equation 1.16b. The pressure is the same for all processes of the 1 atm system, the initial volume is equal to, is 10 cubic feet. And together with the universal constant, they form a composite constant for the processes in the table B.3, with a value of 13.7 pound-mole degrees Rankine, for all gases as it is shown in equation 1.16c. That is the reason why the initial mean molecular speeds are the same for all gases in example B.2. For systems of 4, 7, and 10 atmospheres, the resulting constant of 13.7 pound-mole degrees Rankine is multiplied by 4, 7, and 10, respectively. The situation is very favorable for demonstration purposes, since you have all gases at the same mean molecular speed, in state 1, but different speeds in state 2. See figure B.10. The same heat energy source will accelerate the molecule by different magnitudes, depending on the type of molecule. So, For the system at 1 atm, nitrogen and carbon monoxide are the type of molecule that accelerates the most for the same heat source. Followed by argon, then oxygen, and finally the slowest type of molecule is carbon dioxide. All this results in the difference in final volumes. This means that, depending on the type of molecule, the energy supplied is converted in greater or less movement. For state 2, not only is the temperature between the gases different, but also the volume, so PV/R in equation 1.16b ceases to be a constant. Note that this analysis is impossible to do with the vision of only one state, it is required the two states. The same applies to the processes of the 4 atm pressure system, see figures B.12 and B.13. Where argon is the type of molecule that accelerates the most, followed by carbon monoxide and nitrogen, then oxygen, and lagged behind, at the end is carbon dioxide. Argon displaces nitrogen and carbon monoxide from first place because its Cp remains constant unlike the others, which rise from system to system. One more proof, that the difference between final volumes of gases and therefore, their random molecular speeds and MFV, are defined by the Cp and the delta Hm. Figure B.14 shows the mean molecular speeds for states 1 and 2, for ideal gas and for real gas, in the system at 1 atm where it can be seen that there is no marked difference between ideal gas and real gas. The difference arises in the system for 4 atm, shown in figure B.15, where it can be clearly observed how the behavior of the molecules, both nitrogen and carbon monoxide, move markedly away from the behavior of an ideal gas. However, argon, oxygen and carbon dioxide still behave much like ideal gas. At the point at 4 atm not only the divergence between functions is presented and the tendency of these changes markedly, but also, the non-ideality of some gases is manifested more clearly. The same happens for the system at 7 atm, although the difference is not as marked, as can be seen in figure B.16. Finally, for processes in the system at 10 atm, again the difference between real gas and ideal gas is not distinguished, as can be seen in figure B.17. It can be observed how for the processes of the system at 4 atm, nitrogen and carbon monoxide move markedly away from the ideal gas behavior, just as shown in figure B.15, while the other types of gases' behavior remain very close to that of the ideal gas. The variables MFV, elasticity, and mean molecular speed, are functions of pressure and volume, but while the functions of molecular flow velocity and elasticity undergo a change abrupt in its tendency by increasing the pressure of the system, the function of mean molecular speed does not register a significant change with respect to the other pressure systems. This is because MFV and elasticity are variables that relate both states of the process in the system, state 1 and 2, if we do the same with the mean molecular speed, we obtain the same pattern as the other RGT variables. See figure B.18, the quotient of mean molecular speeds sensitizes the variable, allows us to perceive the effect of pressure on it. That is, if we relate the mean molecular speed with both states, then we can observe the PVT behavior on this variable. The thermodynamic meaning is that pressure altered the relationship between temperatures, and therefore molecular speeds, from one system to another. The same happens with the contraction of gas. This is the reason why equations of state are not accurate, because they analyze an isolated state, do not study the two-state process. Conclusion. The functions of different real gases follow the same trend because this is stipulated by the PVT relationship. The main factor that will define the divergence between functions and the difference between final volumes for the different gases, subject to the same heat source, the same mass, the same pressure, the same initial volume and that have the same initial mean molecular speed, is the momentum enthalpy, delta Hm as a function of the heat capacity, Cp. The scheme B shows a sequence of functions that are involved in the processes present in example B.1 and B2. Begins with the heat source, with equation 1.9, and how it impacts in the momentum enthalpy and in the heat capacity, equations B.0 and 2.3, of the different gases, as the input. These two variables will define the rest of the parameters, here the gases differ among them. They take distance with each other, with the heat as the input and the temperature as the output. Then the sequence here splits in two paths. First, the EER equations 1.17 and 1.21 with temperature as the input and the volume as the output, and finishes this part of sequence with the equations A.2a and A.2b with the volume as the input, and the MFV as the output. And in the other path, the MKT equation A.17, with the temperature as the input and the mean molecular speed as the output. And finishes this part of sequence with the equation A.23 with the mean molecular speed as the input, and the MFV as the output. The Joule-Thomson effect on RGT. N. The modeling of expansion-contraction processes by numerical methods. The Joule-Thomson effect or Joule-Kelvin is a process by which the temperature of a real gas increases or decreases, due to expansion or contraction, carried out at constant enthalpy, or an adiabatic transformation by which no work is extracted. It was described by James Prescott Joule and William Thomson, Lord Kelvin, who established such an effect in 1852 as a result of modifying a previous Joule experiment where a gas expands while keeping the internal energy constant. The classic experiment of the Joule-Thomson effect is shown in figure E.1, where at the beginning of the experiment, a gas contained in a volumetric section to the left of a porous septum, is subjected to a pressure A, higher than another pressure B on the right side, then passes through the septum on the right side. The walls of the entire system are insulated. This process occurs at constant enthalpy. The problem is handled in 3 steps, 2 stages, A and B. In the first step of the process, stage A, the gas starts with the parameters P1A, V1A, T1A, to then be compressed by a piston with a speed V1A, raising its pressure and forcing it to pass through the porous block, in a position delta x/n, of the piston stroke A. Volume 1A is reduced and stage A ends, at conditions P2A, V2A, T2A, and velocity 2A. Stage B starts with the parameters velocity 1b, pressure 1b, volume 1b and temperature 1b. Just when piston A is at position delta x/n of its travel, as well as piston B. Finally, velocity 2b begins to decrease and, when both pistons finish their travels, the gas has the parameters P2b, V2b and T2b. Starting with the EER equation 1.16 and differentiating it, we get equation E.1, then, in stage A, integrate equation E.1, from step 1 to step 2. As shown in equation E.2, and becomes in equation E.3. Or another version is equation E.4. The second term on the left oft equality on the EER equation E.4, shows the molecular kinetic energy, where E subscript K, is the molecular kinetic energy in BTU. E subscript Mk is the molecular kinetic energy divided by the number of moles in BTU per pound mole. For this particular case, the non-ideality does not come from heat transfer, since there is no such a transfer, it comes only from the difference between molecular speeds, of the real gas and the one for the ideal gas, due to intermolecular forces. Here the molecules are not impulsed by heat, but by a force. That is, they are not impulsed by a momentum enthalpy, equation 1.7a, but by a physical momentum. Equation 1.8 if the force applied, and the area, A, are the same throughout stage A, then the pressure is also the same. On the other hand, the work exerted by the piston on a gas, is the work equals the pressure multiplied by delta V. So for this process we have equation E.5. The combination of the equation E.4 with equation E.5 becomes on equation E.6. In stage B, the same procedure is followed as in stage A, to obtain equation E.7. We know that the work done on the gas by the piston in A, is equal to the work done by the gas, on the piston in B, with negative sign, adding equations E.6 and E.7, for the whole process, the result is shown in E.8. In the border between stage A and stage B, there are three hypothetical cases. 1. T2A, equals T1B. 2. T2A, less than T1B. 3. T2A, greater than T1B. For all three cases there is the restriction, the initial temperature is greater than the final temperature. T1A, is greater than T2B. This necessarily implies that molecules that accelerate in A and decelerate in B, do so in such a way that the deceleration is different in magnitude than the acceleration, because for the ideal gas, the molecules accelerate and decelerate by equal magnitude. Now, in step 2, in the hypothetical case where T2A, less than T1B, to assume that the molecular speed continues to grow even when it has already crossed the porous wall and started the expansion, it is contradictory. If the conditions have already changed, it is not logical that the growth trend continues. The trend must vary, either stop growing or start a slowdown. Therefore, the option where T2A, is less than T1B, is ruled out. In figure 1.35, T superscript 2 subscript 1b is the temperature in the assumed case where T2A, is less than T1b, which has already been ruled out. The hypothetical temperature T superscript 1 subscript 1b, is the temperature in the assumed case where T2A is greater than T1b. For this case, it is assumed that right at the border of the stages, instantaneously, the change in molecular tendency arises so that, at that point, suddenly, the temperature and molecular speed which had been growing now instantly decrease. In the suppose that the pores are an obstacle, in the macroscopic perspective, for the microscopic point of view, it is not the same, the temperature is increasing because the collisions are increased, due to the reduction of space, but it happens on both sides equally, so the option where T superscript 1 subscript 1b decreases go against the MKT in the sense that the collisions are increased and the temperature decreases. This case doesn't really happen. In addition, molecules like any particle that has matter, possess inertia, which by definition is the resistance to change in its state of motion. All this contributes to ruling out the supposed case where T2A is greater than T1b. What's more, intermolecular forces, which are very active at the boundary between stages, contribute to the cohesion between molecules, increasing the inertial effect. All of the above leads us to the conclusion that the strongest case is the one that at the border itself, where delta x/n is such that the velocity 2a equals velocity 1b, it is true that T2a equals T1b. Obviously, as the volume increases, and step 2 progresses, this restriction ceases to be valid. Therefore, the fact that T2a equals T1b, means that mean molecular speed in state 2a, is equal to mean molecular speed in state 1b. And therefore that molecular kinetic energy in state 2a, is equal to molecular kinetic energy in state 1b. Therefore, by cancelling equivalent terms, and grouping similar terms, equation E.8 may be rewritten as is shown in equation E.10. Equation E.10 shows precisely the effect of the intermolecular forces on the molecules of the gas, shows how much molecular kinetic energy was converted in molecular potential energy due to intermolecular forces. The quotient on the right side of equality in the equation E.10 yields a negative value because this term represents a balance of kinetic energy throughout the system, which comes out negative, because part of the kinetic energy of stage B was transformed into potential energy, due to the action of intermolecular cohesion. The Joule-Thomson coefficient may be obtained as is shown in equation E.12 or in equation E.13. Example E.1. Nitrogen has a Joule-Thomson coefficient of 0.2 degrees Kelvin per atmosphere at 25 degrees Celsius, 298 degrees Kelvin over a pressure range of 1 to 50 atmospheres. Determine the final temperature of the gas. If the initial temperature is 298 degrees Kelvin and 50 atmospheres pressure, the gas is stored in a vessel and passes through a throttling valve into another tank, which is at a pressure of 1 atmosphere. The information we have is T1A equals 536.4 degrees Rankine. P1A equals 50 atmospheres. P2B equals 1 atmosphere, and the Joule-Thomson coefficient is 0.2 degrees Kelvin per atmosphere. From equation A.18 we obtain equation E.13. Combining equation E.12 with equation E.13 and solving for the molecular kinetic energy in state 2b, becomes an equation E.14. To solve equation E.14 it is necessary to transform the term on the extreme right side of the equation, so that it has the units equivalent to the other term. For this, we obtain the kinetic energy equivalent to that temperature as is shown in equation E.15. This energy represents the amount of kinetic energy converted into potential energy due to intermolecular forces. Combining equation E.14 with equation E.15 yields equations E.16 and E.17. The temperature T2b is that temperature at which the molecular kinetic energy in state 2b develops. Therefore, it can be obtained from the equation A.18. And its value is 518.76 degrees Rankine, 288.20 degrees Kelvin. The final temperature drops about 10 degrees Kelvin, with respect to the initial temperature, delta T equals minus 9.8 degrees Kelvin. Example E.2. Nitrogen is in a vessel at a pressure such that it is at 25 degrees Celsius, 298 degrees Kelvin. To then have an isenthalpic expansion until reaching 77 degrees Kelvin at atmospheric pressure. Determine the initial pressure. The information we have is T1A equals 298 degrees Kelvin, T2B equals 77 degrees Kelvin, P2B equals 1 atmosphere. From equation E.12 we have the equation E.18. To know the initial pressure, it proceeds to integrate equation E.18, then yields equation E.19. In the example above, a constant Joule-Thomson coefficient was used for a specific pressure range, 1 to 50 atmospheres, at 25 degrees Celsius, but we know that the coefficient μ is actually a function of both pressure and temperature. For this example, the coefficient is not constant, see figures E.4 and E.5. In order to take out the coefficient from the integral, we resort to the already used, a procedure similar to that used for the mean heat capacity. That is, it seeks to obtain a mean Joule-Thomson coefficient. This mean coefficient is obtained with the mean value of the pressure, in μ as a function of mean xp. Where the mean xp is the average of the values of pressure, graphed in figure E.5. That way, it is already possible to handle it as a constant value in equation E.20. From the data used to make the graph of the coefficient μ, in figure E.5, it is obtained the mean xp that is equal to 360.9 atmospheres. Where n equals 10. Figure E.5 shows the point of the mean xp and the respective value of mean μ. The initial pressure is determined by solving for P1A, in the equation E.20. P1A is equal to 357.45 atmospheres. The modeling of expansion-contraction processes by numerical methods. Once the expansion-contraction processes are defined as a concentric layer movement and molecular flow, the compressible fluid flow theory can be applied to this process. We know that the mathematical models for compressible flow vary according to the type of flow, whether supersonic, sonic or subsonic. Although considerable speeds could be developed, the truth is that the subsonic flow is the most common for the expansion-contraction of a gas. Common functions used for compressible fluid flow are phi and psi. These functions are called velocity potential and the stream function, respectively. If we define density as a continued property and use Eulerian description of fluid flow, we can state that this is both a function of position and time. Another way of describing conservation of momentum that helps us develop the approach is the one shown in equation E21. Rearranging, we have equation E.22. If we conveniently define the velocity vector, v equals c, where c is the velocity of sound, we get equation E.23. The Euler's equation for a steady motion is shown in equation E.24, and is the same equation 1.8, that we have already seen. Combining equation E.24 with equation E.23 and solving for c, yields equation E.25a. An alternative equation combining equation E.23 with equation 1.7a results in equation E.25b. Equation 1.7a, in vector form, becomes equation E.26a, where u is the horizontal component and v, the vertical component of the velocity vector. These components may be written as a function of the velocity potential and the stream function, respectively. As shown in equation E.27a, for the stream function, and equation E.27b, for the velocity potential. And there is an additional notation as the one we present here. Then equation 1.7a, may be written as shown in equation E.26b. The combination of equation E.26b with equation E.25b results in equation E.28. The differentiation of equation E.28 with respect to x becomes equation E.29a. And respect to y, becomes equation E.29b. The continuity equation for this notation is presented in equation E.30. The combination of equation E.29a, and equation E.29b, with equation E.30, results in equation E.31. The term on the right side of equation E.31, is a function of time, if we define it as a function g, and multiply the same equation by minus c squared, we get equation E.32a. Equation E.32a is the general equation that governs the subsonic compressible fluid flow with the velocity potential. And it is the equation that we use to modeling the expansion-contraction processes. But, if for convenience, we deal with equation E.32a, for the steady state, at the moment, then becomes equation E.32b. The function for c is presented in equation E.33. Equation E.33 is very useful because, to solve equation E.32 by numerical methods, it is appropriate to use an iterative procedure, and equation E.33 is used to obtain the speed of sound used in equation E.32b in each iteration. The boundary conditions of equation E.32b are the Newman and Dirichlet, and are presented in equations E.34a and E.34b, respectively. Problem description. We choose to use the finite element method FEM to model the process. Here, we will only present a shallow review in the approach of the problem. To see the complete approach, you must consult the RGT book. The solution procedure consists of discretizing the dominion in elements and formulating corresponding equations. There are some iterative linearization techniques to solve nonlinear partial equations systems like the Newton-Raphson iteration technique, or the Poisson iteration technique. The compressibility of gas is represented by the nonlinearity of equations in the system. A common way to treat the compressibility effect is using an iterative linearization algorithm. Nonlinear terms of the equation are sent to right side of equality and evaluated for a previous solution, from the past iteration, similar to a forcing function. This method was used by Rayleigh in 1916 for compressible flow analysis using complex variables techniques. From the development of equation E.32b we have equation E.35. When grouping the nonlinear terms on one side of equality, becomes equation E.36. For the iterative procedure, function phi is replaced by function phi superscript n, that is, the function by iteration n, previous to iteration n plus 1. Equation E.36 may be written as shown in equation E.37. The equation E.37 is the Poisson equation, as long as it is used in an iterative form. F1 is the forcing function for the previous iteration n. The associated functional equivalent to the field equation E.37 and its boundary conditions, equations E.34a, and E.34b, is the one presented in equation E.38. where uppercase gamma 1, that belongs to the dominion of omega, and the function f, represent the Newman boundary condition. And in the boundary uppercase gamma 2, the function phi is equal to a constant. The physical meaning of the function phi, being constant, is that the change of the variable with respect to the vertical is 0, and the velocity vector is perpendicular to the transverse surface. For example, figure E.6 shows an expansion piece where the function phi can be seen in some points of the domain. The disturbance here is the change in areas caused by the change in the solid border angles. For phi to be constant, it must be far from the disturbance, and the border uppercase gamma 2 can be placed there. The Newman boundary must be placed enough far from disturbance that phi be constant, and the border uppercase gamma 1 can be placed there. This condition represents the input velocity. The phi function starts being constant. But once it gets to the disturbance, stop being constant, and when it moves away, returns to be constant. The forcing function in equation E.37 is shown in equation E.41. And the function of the velocity of sound is shown in equation E.42. The contribution of an element E to the functional in the domain, omega, is I superscript E. Then, the sum contributions is presented in equation E.43. E is the total number of elements on the domain. The functional in the element I superscript E is shown in equation E.44. Note that only superscript n from the previous iteration was included, superscript n plus 1 was excluded for better readability. The second partial's derivatives in equation E.41 may be defined as the ones written in equation E.45, where the corresponding Jacobian, J2 superscript E, is presented in equation E.46. Solution to compressible flow around a circular cylinder. The problem consists of obtaining the velocity profiles and analyzing the distribution of pressures and densities in the flow domain around the cylinder. Figure E.7 shows the distribution of the velocity vectors in the domain. As could be expected, the greatest magnitude vectors are those located in area points colored red. Velocities up to 2.14 are reached for u equals 1. In this region, velocity was doubled with respect to the input speed to the system. In figure E.7 we can see that the vectors colored green have a velocity of more or less 1. As this vectors approximate to the lower region of the circumference, velocity start to reduce. The vector colored light blue reach a velocity up to 0,7 and down to 0.36. But the vectors that approximate to the lower corner are those colored purple. Their velocities are from 0.36 down to 0. In the other side, the vectors that approximate to the upper region of the circumference are colored yellow, orange and red, and have velocities from 1.07 up to 2.14. Solution to compressible flow through a sinuosity. Figure E.8 shows the distribution of the velocity vectors in the domain. In figure E.8 we can see that for a input speed, u equals 1000 feet per second, the vectors that fall down in the sinuosity reduce its velocities under 699 feet per second. The vectors that reach the top region of the sinuosity have velocities up to 1300 feet per second. Formulation for real gas. The formulations shown in this work are used to pose the solution to the expansion-contraction of a real gas. For that, two concepts that make up the thermodynamic phenomenon are handled: the diffusion of heat in the gas and the arisen convection. Suppose the system seen in figure 1.1. The diffusion is handled with equation 1.3, in matrix form. It may be written as shown in equation E.47. The procedure is iterative. The matrix solution T superscript n plus 1 is obtained with equation 6.20. Using this value, we obtain the densities ρ superscript n plus 1. Once the densities are obtained, G is calculated. Note that the data of iteration n are known. Finally, from the term of the center of equation E.49, solution matrix phi is calculated with equation E.48. With the velocity potential, pressure profiles P and velocity components U' and V' are obtained. All this for a period delta t. For the next period, the mesh is modified, and the process is continued. Literature presents various formulations for the FEM, for the different types of heat transfer, conduction, convection, etc. Like the one presented in the equations from E.51 to E.54. The element function uppercase Q is the equivalent of element function F1 in equation E.41, and the element function lowercase q is the equivalent of element function F in equation E.39, and are shown in equations E.55 and E.56 respectively. The boundary conditions are presented in equation E.57. The Newman boundary conditions for the heat transfer, for the equation E.51, applied to this case, are the ones shown in equation E.58. And for the MFV, for the equation E.48, are shown in equation E59. In figure E.9, the flux Q is normal to a plane perpendicular to the tangent line to the curve, uppercase gamma prime, 2, and goes in the opposite direction of U. This flux and U do not exist in the borders, uppercase gamma prime, 3, and gamma prime 1. The Dirichlet boundary condition are placed in the lines, uppercase gamma prime, 3, and gamma prime 1, where temperature and the function phi, there, are constant. All this for a period delta t. For the next period, the mesh is modified, and the process is continued.